Okay, we looked at the basic definitions. We came up with a list of what we thought these industrial robots could do. Um, we looked at the basic makeup, and then we went around to all the robots and looked at their controllers. We saw the robot, the power source. The power source for all these robots, by the way, the end of arm tool is powered by pneumatics on all our robots. And then the actual power source for the controller and the robot itself is electric. Talked about the axis. Are we okay there? So we got all our axis, all our robots are what we call 6-axis. We can also call them 6 joints, or we can also call them degrees of freedom, right? 6 degrees of freedom. Are you okay there? And the controller basically runs the whole system. Then we started looking at the T-Spin. This is where you do what you call online programming. With Intro to Robotics, right? I know, well, y'all had Intro to Robotics. The other method we use is what we call offline programming. And that's where the real power of the little Lego robot comes into play, is offline programming, because it's such a small unit. What you'll find out is that on most industrial robots, you can actually do more stuff with the T-Spin than you can with an offline program. But that's not always the case. ABB has a thing called Robot Studio, which you can do. You can actually do more with that, or it's easier to do. So the simulation package we use is one called MotoSim, and it's on your computer, but you can't load it up because it's copyrighted with a USB key. But what we do with this is we program the robot through a simulation. So if you're taking the simulation class in a T2, then this is what you're going to play around with. Yeah, but I'll take care of that right now. I'll show you what. So notice this is the work cell for the Motoman robot, which is one right behind Josh. Of course, what you do in your 3D model is you can set what we call the opacity of the unit, so you can make stuff that's solid so you can see through it. Of course, you can't see through those metal bars up there. It just makes it easier to write your program. And what we do is we have a simulated T-Spin, and what we can do is we can jog the robot. You know, see it? And this is the model now you don't make the model of the robot. The model of the robots are supplied with the simulation package. But what you have to do is develop the model for the work cell. And then once you develop the model for the work cell, you place the robot in there. And you teach it just like you would teach it over there. So you have different ways you can jog it, which we'll talk about. But and this is actually a robot program right here. And we can come over here and we can run the program. And this is the one y'all might have seen run over there where it's doing the demonstration. So this program was actually run on a simulation. And then what we do is once you get it developed on your simulation, you can take the simulation program and go and upload it into the robot. So what you're doing is when you're writing the program, the robot is not offline, and you're going to learn that this semester. It takes a while to develop programs. And I don't care what language you're writing programs in, they don't just pop up there. And you make a lot of mistakes and you do things wrong. We'll show you how to, of course, edit programs and stuff like that. It's very, very important. And you'll see how long it takes to write a program. Mercedes down there has almost 1,300 robots. And you can imagine how many people it would take and how long the robots would be offline if they had to reprogram those robots online. So most of your big applications, your programs are actually developed on a simulation. and they get all the bugs out of the simulation. They make sure it's no collision. What's nice about a simulation is kind of like a video game. You know, you can get killed in a video game and it don't hurt you. So simulations, we can collide, we can make mistakes, and we can do a lot of things, but it's not going to hurt anything because it's a what? Simulation. So we can turn on what they call collision detection. We can set up collision detection, and we can tell when the robot is going to collide, and then we can make those corrections in the simulation without what? Without actually colliding the robot. So this would be offline programming for these robots. Very, very powerful. What we could do. So, but we're not going to do that this term or this mini term. If you're in the simulation class, which is in T2, then this is what you'll play around with. So we name, create online programs, edit, copy programs. Of course, we're going to have to learn how to copy and do backups. We can configure the system, but you're not going to do any system configuration here. We select modes of operation, which we'll look at in a minute. Select user levels. It's kind of like on this network right here. If you try to install a program on this computer, it won't let you because you don't have the rights to do it. And you have the same thing on these robots over there. We call them user levels. You can set the speed. You can set up the display, and of course, we'll start off by doing what? Learning how to jog the robot. This is the teach pendant for the Motorman robot, if this is the one you get. Of course, this diagram is inside the manual. And of course, what you're going to use is you're going to use the manuals that come with the robot. Because that's what you would have. You know, if you was working at a job, that's what you'd have. You needed to figure out something. How are you going to figure out how to do that? We're going to figure that out with the manuals that come with the robot, right? Y'all understand that? So this guy here has some touchscreen capabilities, but it's still also got a lot of keys. This is where we're going to move the robot at. We're going to talk about a coordinate system before long, but this is what you're going to have to learn how to use on your robot. This is the robot for the Kuka robot. This is the teach pendant for the Kuka robot. Of course, this guy has a full-size keyboard on it, which I really like, because I don't know if y'all remember the old days when before phones had touch screens. They actually had buttons on it, and what you had when you tried to text is every button represented 3 letters. And what did you have to do? You select the key and you keep hitting until you got the letter you wanted. Of course, now just about all our computers have touch screens. Some of the robots still use that. The Fanuc still uses that feature where you got to go through sets of numbers. The Motorman, since it's got a touch screen, it'll pop up a simulated keyboard just like your cell phone does. This is the teach pendant for the Fanuc robot. It does not have. So this guy here doesn't have a touch screen on it. So if they don't have a touch screen, then everything you do is going to have to be done on one of these push buttons around the side and down here on this guy. The Fanuc, we don't have that one. This has a touch screen on it, so I mean some of the things you're going to do with the touch screen, some of the things you're not going to do. This is the this is the Motorman again. Sorry, this is the first one we got. Somebody's turned on the touch screen on my computer. So. This is the teach pendant for a little Mitsubishi robot, which y'all not going to play around with this semester. This is the one we have on our production line. Did we leave out any? So there's the Kuka, there's the Fanuc, there's the Motorman, and I don't have the ADB. So I'll have to find that and put that in there. So the input-output section, we're not going to deal with that much this semester, but we're going to have to do, we're not going to connect things up to it. In the industrial robotics class, we actually let you connect inputs and outputs up, which is pretty neat. Here we're just going to understand that to get information into the robot controller and out of the robot controller, we use something called I/O ports. So this keyboard on your computer is not connected to the computer. Well, it's not connected to the processor. It's connected to an input port. So we'd follow a cable and we'd see that it plugs into the back of the computer, and that's an input port. The display would be connected to an output port. So we have an external output on my computer right there. So USB is a portal. Y'all understand that? So it's ports. So, but it's unique. Robot sensors are connected to the ports. So that means your sensors inside the robot that's sensing the speed of the robot and the position of the robot are connected to ports. Of course, those ports are dedicated. Production area sensors. So when we go over there and look at the Amatro line and the Festo line, we'll see that the robot is actually responding to sensors that's out inside the production area. The robot teaching station or the teach pendant is connected to ports. This may be part of the attached computer or the controller itself. Most of your robot controllers allow other devices to be attached to it, like PLCs and stuff like that, where we can actually add additional ports to the robot through other things besides the actual robot controller itself. Are we okay? This is the controller for the ABB. So the unit I showed y'all is this guy right here. And then of course you have the power supplies and you have the big old heat sinks and stuff down in here that's actually got the devices that actually control the motors on the robot. This is a PLC that's actually mounted inside the cabinet. We don't have that on our robot, but this guy here can communicate. So this would add all types of inputs and outputs to the robot. We'll show y'all this on the big FANUC. So they have a big DeviceNet card up there that allows us to connect a ton of stuff to the robot controller without actually supporting the ports on the robot itself. This is the FANUC controller that we looked at. This is the 31A. The new robot has a 30B on it, which they look identical, by the way, except this one we back up and save stuff on a compact flash card. Instead of talking about it, let me look at that little old thing in the center. That means we're paused. What I liked about the Tegrity, it had big old pause up there in the upper right hand corner. So this is basically the makeup of the controller. So we have an input-output section where we hook up our production sensors, where we hook up production equipment, the teaching device, mass storage devices. This says cassette tape, so you can tell how old this guy here. When's the last time y'all saw a cassette tape? Some of y'all probably don't know what a cassette looks like. If it supports a printer, it would hook up here, and then other computer hardware would go to this. We have our servo devices interface, so this would be the interface for all your servo motors and everything. Y'all know what a servo motor is, right? Can you talk about that? What's a servo motor? Yeah, it's a motor that provides feedback. Solid state memory would be in there. Of course, we got to have a cooling system. We talked a little bit about that, didn't we? By the way, y'all have access to these PowerPoints, right? I know that. Robot power. The robot, so what powers the controller? What type of power source do we have for the controller? Electric, because it's a computer, right? You understand that. When we get to the robot, then the robot could either be electric, it could be hydraulic, or it could be pneumatic. Of course, electric is the primary power source because it's all over the place, right? So I don't have to have much to use electricity, especially in the United States. The power grid in the USA is very, very extensive. Hydraulics. What is hydraulics? Yeah, we create power with not fluid, We create power. A fluid is stuff that's in motion. So air is considered to be a fluid. Y'all understand that? A lot of people don't understand that until you get into what they call fluid power. I didn't know that when I first started hearing that. I thought fluids were liquid, but they're not. So fluids can either be a gas or it could be a liquid. So if you look up fluid power, that's what it's going to say. Hydraulics use liquid as the fluid. Pneumatics use gases as the fluid. Of course, the predominant gas we use is air, which actually is a combination of gases, right? Predominantly oxygen and nitrogen, right? So, why would I use hydraulic? Well, greater pressures. Yeah. So the amount of force we generate in a fluid system, they call it Pascal's law, by the way. So force, how much force? So force is something that you apply to cause it to change shapes or change directions, right? It's equal to the pressure that you're applying times the area you're applying that pressure to. So we can't say it produces more force because I could have a pneumatic one that's got a area that size that's developing 10,000 pounds of force, and I could have a pneumatic cylinder that's that big generating 10,000 pounds of force, right? So what we do with hydraulics is we have the ability to produce more what? Pressure. So we can't have force unless we have a pressure. So pressure is what's actually doing the pushing. Force is what the pressure generates. Y'all understand the difference? A lot of people don't. A lot of people think pressure and force are the same, but they're not. So what's the advantage of hydraulics is we have the ability to use extremely high pressures. So that means the actuator's area can be smaller to produce the same force, right? So what's nice about hydraulics is the size of the actuators. So I could generate the same force with pneumatics. It's just that the actuators would have to be what? Real big. Right? Y'all understand? The biggest pressure I ever dealt with out of UST for pneumatics was 200 psi. That was the maximum pressure. Up at Bridgestone though, they run a high pressure of 600 psi. I'd never seen that before. 600 psi. So if it's 600 psi, then that means, I could generate 600 pounds of force pushing against 1 square inch of area. Hydraulics, our hydraulic trainers, we used to run at 1,000 psi here on campus. The highest pressure that I dealt with was 3,000 psi. So 3,000 psi means I can have an actuator that had 1 inch of area and generate 3,000 pounds of force. Now the problem we have with pressurizing gases is when gases come under pressure, eventually they'll turn into a liquid. Y'all understand that? We buy liquid oxygen all the time. We buy CO2. We used to play paintball when we had our own field station. And, if you're a welder, you go out and buy those gases. Those are all liquids. And how do they turn them into liquids? They just pressurize them. Another problem we have with air is that air itself carries a bunch of impurities. So that means normally before we run it in, we got to filter it. And then plus air has a lot of moisture in it. Liquids are uncompressible. So what does that mean? Yeah, in fluid power, I've got this big old syringe that I got, and you can fill that sucker up with water, and you can stop it up, and you can try to push the plunger down, and it don't move because it doesn't compress. Right? You understand? We can empty the water out of there, and we can fill it full of air, and I can plug it up. And before I start getting a lot of pressure, I'm gonna have to push down on that thing a lot. Right? You understand? So the problem we have with gases is that gases compress when we try to use them. So that means before you create a pressure, what do you have to do? You have to compress them. You have to get rid of that compressibility. So uncompressible means these guys here are very, very smooth. As soon as I actuate it or put fluid into the pressure, if the flow of the liquid is smooth, then it's going to be smooth. I can control it since it's uncompressible. If I can control the flow, so we got two things that we're concerned with. We got how fast something moves, and then how much force we can generate. Y'all know what determines the speed? Y'all know what determines the speed of a fluid system? Y'all know what determines the speed? Well, what determines the speed is how fast the fluid's moving. So the flow rate determines the speed, right? You understand. The pressure determines the what? The force. You understand that? Well, since hydraulic fluid is uncompressible, if we've got a flow control valve, we can control that speed precisely. Pneumatics, as soon as it starts moving, it wants to uncompress. So what happens is that when it hits against the actuator, it's going to be jerky, right? So it's going to create the pressure, the thing's going to move, and then what's it got to do? So as soon as the actuator moves, it's got to come in and hit it again. So pneumatic cylinders, if you don't do something with the flow control, and it's hard to control speed. You know, you can get a rough idea of a speed control with a pneumatic system. Pneumatics can be jerky if you don't do anything with them. And the pneumatics, they'll talk about meter in and meter out. So pneumatics, what we have to do is meter out, which works out okay. So pneumatics, now so uncompressible, smooth motions, easy to control the flow rate. What's the disadvantage of hydraulics? Why don't they use hydraulics all over the place? Huh? Yeah, it's messy. You know, it's almost impossible to get a system that don't leak, right? Y'all understand that? Hydraulics usually use oils. The oils are very dangerous. They're usually very poisonous. You know, if you go out and drink motor oil, what's going to happen? You're probably going to die, right? So oils are very dangerous. The pressures are so high. We knew a guy that got into a pinhole, came into the hydraulic system, and when he hit it, it went into his thumb, and that fluid got in there. Of course, it sealed up almost instantly, and he almost lost his arm because of that. He didn't, but he was lucky because that fluid got into his bloodstream and caused all types of problems. So this stuff is dangerous. If you get a leak, it's oils. Oils are very slippery. I don't know if you've been around a hydraulic system before. We used to teach we used to have hydraulic trains. And they had quick disconnects on them so you could repipe them and mount different things on the thing. It was really, really neat. But the problem is that we couldn't keep oil out. I mean, the oil was all over the place. We eventually had to come in and put a floor in that had holes all in it. That was a temporary floor, so the fluid would go down into it. So what we used to do is we used to teach fluid power. We taught pneumatics and hydraulics, but all the labs were done on hydraulic trainers, and we got rid of those things. So now we have pneumatic trainers. So we don't have to worry about pneumatics. If you get a leak in a pneumatic system, you might reduce the pressure, right? You understand. You might not get the pressure or the flow, but all you get is just a you know, it's very hard to get a pneumatic system, especially if you got quick disconnects where you don't hear that. Pneumatics is a well understood technology. We run lower, so low pressures is an advantage sometimes, and it's a disadvantage at other times. So low pressures mean they're not going to be as dangerous, right? You understand? Low pressures means we can use plastic piping instead of metal piping. So in a hydraulic system, they're either going to use metal, or they're going to use in their piping, or they're going to use reinforced rubber tubing, and those things are expensive. I don't know if you've ever, so that's what your air conditioning system in your car is. Most of the metal tubing on that compressor is metal. And then when they have to go flex, like going from your engine over into your firewall, or going from, the compressor over to the first metal tubing, those are flexible tubing. If one of those things go out, you better be prepared, because that's high pressure tubing. The pneumatics, so all our systems we run them on about, 50, 60 PSI, which is pretty standard for pneumatics. So what can we use for tubing? Yeah, you look at all the tubing on all these robots running the gripper. It's just plastic, standard plastic tube. So that means the system itself is a lot cheaper, right? The higher the pressure, the more expensive it's going to get to install. And of course, another big advantage is once we get through with the gas, what can we do? Yeah. On a hydraulic system, we have to have at least two piping. Not only do we have to take the fluid out, we got to do what? We got to bring it back and put it in a tank. So and we can find these. I don't know if I put some pictures in here. Undoubtedly I did. And they still make hydraulic robots, and they still make pneumatic robots. And of course, we could probably go to the internet and look up a hydraulic robot. And we should see a few. Now, what's nice about a hydraulic robot is that we can run it in real gaseous environments too, right? I don't know if that's hydraulic or not. I don't know what they're doing there. These all the images I brought up, these look like they're homemade. So that looks like homemade, don't it? Can't tell what that is. But you got all this piping. See all the piping? This I don't even know if this would be considered a robot. Looks like it's a. That guy's neat. This would probably be. This could be a hydraulic robot, a mobile robot. I don't know what these are. I can't tell, but it's definitely hydraulic. So if we run it inside a gaseous environment, then we don't want to use electricity, right? Does that make sense? Yeah, this brings up the same ones. Now we've got several pneumatic robots over there. So these are pneumatic robots. So they also would be safe in environmental. That's not a pneumatic robot, I don't think. That would be one. There's a rectangular pneumatic robot. So we've got 2 through 4 over here. We got 4 on our 2 production. No, we got 3 on our production lines that are ran by pneumatics. That's not a pneumatic robot. They bought one of those things and put it down in the tech center in Columbiana. And the last time I looked, nobody knows how to program it. She's sitting down. End of arm tooling, everybody okay there? So this is a lot of this is a repeat for intro. These are the devices that attach to, also called an end effector, also called a tool. Just about all textbooks you go is either going to call it this or they're going to call it that. This is a device attached to the robot flange designed to interact with the environment and to do what the robot was established to do. A lot of people think that a gripper and an end arm tool are the same thing. Is that true? It's a type of end arm tool. Everybody understand that? This is some grippers, and these are just a bunch of pieces. Some of our robots have suction cups on them. Some of them have grippers. Some of them have, this is a drill. This is a spray painter. This is a milling machine. This looks like it would be a form of gripper. This would be a form of gripper. Of course, this is a welding torch. So the end of arm tool is what you mount on that flange to do what you bought that robot to do. Pigeon device, computer simulation. We'll look at that if you're in the manufacturing and computer simulation class in the T2. And you'll deal with that. We're going to do all our programming through Teachpin. We refer to that as online programming. Are you okay? So we're going to do online programming this mini term. If you're in the manufacturing and computer simulation class, you'll look at some offline programming. Data storage devices, standard cassette tapes. That would be an extremely old robot. Mini cassette tapes would be on a robot. Floppy disks could be true. Hard drives could be true. CD, ROM, and DVD. PC cards, which is PCMCIA. That's what I've been trying to say. Those are still out there on robots that are not really old, but that would probably be 2 generations back of what's coming out now. Compact flash is very, very popular on probably one generation back from where. And then the current generation robots use USB. Now USB is okay, but remember USB is extremely slow, right? You understand? So degrees of freedom, everybody okay on here? So all our robots that we'll be dealing with is run 6 degrees of freedom. Should also say 6 joints, right? Or we could also say 6 axes. And those terms are interchangeable. Everybody okay on the orientation axis and the positional axis? Y'all all had intro when we taught that there. Any question on those? So what's the function of the orientation axis? The orientation axis. So here's my orientation axis right here. So what's only moving now? My hand, right? Okay, these are my positional axes. So the positional axis on my arm would be my shoulder and my elbow. The one joint in my elbow. So our elbow, just like our shoulder serves 2 functions. We can tilt with it and we can rotate with it, right? Also on our elbow, we can do things. We can do 2 things. We can tilt with it and we can rotate with it. Now our wrist, we can do 1 thing. That's all we can do. So you can't rotate your wrist. So we rotate right here. So on our robot, axis 1 and 2 mimics the shoulder. Axis 3 and 4 mimics the elbow. Axis 5 is the wrist. and then our robots can rotate the wrist. So our robots can do one thing with the arm, not the hand. So this is our advantage. Of course, we're very, very mobile with how we move, right? So that's two advantages. On ours, the orientation axis will be axis 4, 5, and 6. Because notice when I move these, the only thing, my arm itself is not changing position. When I move these, the only thing I'm moving is my hand. When I move my elbow here, which would be axis 3, and when I move these, which would be axis 1 and 2, I'm moving my whole arm, right? So axis 1, 2, and 3 are considered on a 6-axis robot. Axis 1, 2, and 3 are considered to be your positional axis, and then axis 4, 5, and 6 are your orientation axis. And this says, a little note out there says, may be mounted on a linear movement. So here's our positional axis, 1, 2, 3. Here's our orientation axis, 4, 5, 6. Are we okay? Of course, the orientation axis. So what we're going to have to pick up, we'll talk about that in a minute. Work envelope, everybody okay with that? Also called the workspace. Any questions on that? That was from the last class. We call this the envelope. Everybody okay? This is our envelope, and this would be an example of an envelope for a jointed spherical robot. Tool center point at the end of the tool. Point of action for the end of arm tool. So I almost messed up then. The tool center point does not have to be on the tool. The tool center point is what you're trying to position. So this right here, what would the tool center point be? Well, what I'm trying to position is I'm trying to position this point right there. So the tool center point would not even be part of the tool. On a gripper, all ours use parallel grippers. What am I trying to position? I'm trying to position this point right here. That's the tool center point. So the tool center point on these grippers never are even touched by the tool, because these grippers don't close all the way together. On none of our robots, the grippers actually go. So on ours, this would be the tool center point right here. Now on a welding torch, tool center point would be, if it's a wire welder, it wouldn't even be there. It would be the tip of the wire, because that's what you're trying to position. You're trying to position that wire tip. These guys are very, very precise. What's really neat is we'll see some videos where they actually use the wire as a sensor. So they don't put power on it. They use it as a touch sensor. But those robots you'll see, before they use it, they'll swing around, they'll feed wire out, and then they have a clipper that clips it to an exact length. And then once it's at an exact length, then we can use that to measure stuff, which is pretty neat. So the tool center point, what is the tool center point? It's the point of action of the tool. The point on the tool or in space that performs the work for which the robot was purchased to position. Must be positioned exactly in order for the tooling to perform the job successfully. Now, when is the tool center point important? Well, by default, by the way, when you buy your robot, the tool center point is in the middle of the mounting plate. So when I buy a robot from KUKA, they have no idea what tool I'm going to mount on that. So that mounting plate that's out there on the tool, that's got all the little tiny screw holes in it, the tool center point is going to be exactly in the center. That's where it's set by default. So what we'll do this semester, we won't let y'all do it individually. If you take the industrial robot class, you will. But what we'll do in this class is we'll set a tool center point, but we'll do it as a class. Now, once you set a tool center point, normally the speed is recorded relative to the tool center point. Y'all understand? So if I'm moving my tool like this, and my tool center point's like that, and I say 100 millimeters back here, that sucker out here is going to be moving a lot faster than that 100 millimeters, right? Y'all understand that? So if I'm trying to control the exact speed of the tool center point, then I have to do what? I have to set it, right? Sleep, go out in the car. I'm sleeping in the car. I'm alive. I don't mind saying that. I've done that a long time. Don't go to sleep. Think you understand that. We were taking classes in the military. The instructor had two big old garbage can lids. And we didn't know what to use it for until that person fell asleep. He went sneaking back there with them two big old garbage can lids. Boom, boom. It scared me and I was awake. So, don't go to sleep. Don't go to sleep in my classes. I don't know about other instructors, but, go out in your car, go to sleep. These benches back here are pretty full. Yeah, that's why I usually tell people to go to sleep on the bench back there. I was in the Navy. In the Navy. So there's the one that got me started in the career I'm in now. I was working at a grocery store. So I'd probably be managing a grocery store by now. I'm not, because the Navy decided I needed to go into the electrical trade. And we'll show you how you can tell the tool center point hadn't been set when we start looking at what we call roll, pitch, and yaw. We learn about that. So if you see a question on the test said the tool center point is always at the tip of the tool, what's that going to be? That's going to be false, right? Classifications, we did this in the other class. Everybody here's had the intro, so we go through these pretty fast. But you got to understand, like Brandy, she didn't show up today. She hadn't had that other class yet, so that's why we go back and review. There's no prerequisite for this course. Robots are often classified according to their envelope. We have Cartesian or rectangular. We have cylindrical. We have spherical. We have what we refer to as jointed spherical, but it's actually spread out there a long way. And so, which one would be which? What would this guy right here do? Let me get my pen up there first. Cartesian or rectangular. What would this guy be? Yeah, this is going to be a spherical. As soon as we do the tilt, now what's this guy going to be? Yeah, cylindrical. And I ran out of room. And what would this be? Yeah, this is what we'll refer to as jointed spherical. And of course, this is given in the shape of this guy right here. So when you look at the data sheet, and it really surprised me when I had the people in Intro to Robotics do all those specifications. it looks like they didn't know what it was, and they just come back and just write stuff. So all our robots are jointed spherical robots. So somebody put cylindrical, somebody would put rectangular, and they just look like they said, well, they can't all be the same. Under the power source for the robot, we had some people put hydraulic, we had some people put pneumatic, and all ours are electric, right? So what would this guy be? Yeah, rectangular. So we have a couple of rectangular robots that we'll look at. This would be what? Cylindrical, we don't have any of these available. This would be spherical, and we don't show it jointed spherical. Pick sequence, this would be like a Class A or Class B robot. Usually fixed sequence robots usually depend on hard stops that you can move. A variable sequence is pick and place. And what is pick and place? Just pick, yeah, it's pretty simple. Playback, I'm not really sure what that means. That came out of the book. Numerically control. Some of our robots actually use PLCs. They're actually programmed with PLCs. So those would be intelligent. Of course, all our robots are intelligent. All our robots are closed loop. Some of them kind of use a combination of two. We'll go around and look at some of them in a minute to see what they're doing. Everybody okay on these? Accuracy, repeatability, payload, and speed specifications of the robot? Any questions on those? Which one's very seldom used anymore? Y'all did the worksheet. Yeah, accuracy. Accuracy is very seldom used because why? Because it's a program. It's a programming feature, right? You understand? So this says, okay, it says to what degree to which the robot can move the tool center point in the work envelope when the commands are entered into the controller from the T-spin. So the robot could be very accurate, but you might not be. So you'd be blaming the robot for being not accurate, and it's you the one that can't, you can't get your thumb off the jog button. These guys are very, very, very accurate, but we get a feel of that from this measurement right here. So repeatability, what's repeatability? This is how precisely or accurately it will return to the point once it's been taught. So that way, if you taught the point wrong, it's still going to go back to that point, but it's going to have an extremely high degree of what? Repeatability. All these robots are within the nanometers, all the small robots. The big robot is 100 microns. Range, this is also referred to as reach, too, by the way. And then vertical range, this is the range of all axes given in degrees. I don't know why I did. Robot mass is going to be specified. What's that? That's going to be the weight of the robot itself, not the payload. Vertical reach and horizontal reach, so might not necessarily be the same, especially on a jointed spherical robot. So when you buy a robot, these are some things you're going to need to know. You're going to need to know the payload. What is the payload? Minus the end of arm tool. So the end of arm tool is going to take away from the actual payload the robot can pick up, right? So the payload is how much that robot can pick up, not including the tool. Degrees of freedom, everybody okay there? Also could be called what? Axis and joint. The drive power, what drives the robot, not the controller. Repeatability, accuracy, we don't see much anymore. It's very important to understand the work cell dimensions You know, that'd be awful. You bought a robot, paid $100,000 for it, and it can't reach what you need to reach. Or what you need is outside that envelope, right? You understand? Speed. You buy a robot and you expected it to do it this speed and you can't reach that speed. Well, you bought the wrong robot. You should have bought a faster robot, right? Memory capacity. You want to put 50,000 lines of code in there and you didn't buy one with enough memory capacity to handle 50,000 lines. Well, that's going to be awful too, right? Programming supported. You know, we have a big problem with companies, especially in PLCs, where they don't keep buying the same PLC. They just buy the lowest bidder. And then you end up with all of them running basically different. They all do the same thing, but they all do it a little different. So now your people that's doing your PLCs has got to take time to figure out how this guy does it, right? So if you had 15 different robots out there and you're expecting one person to program it, it's like this right here. So even me, you'll see me go over there every once in a while, and it'll take me a little while to figure out how to do it on that robot. I know I can do it. It's just I got to pull it out of my memory because it's a different robot, right? You understand? So you're out there learning one robot. How many do I have to keep? I have to keep it 6, right? Which makes it real hard on me. By the way, to get the grant, we were going to try to buy all the same robots. But this is a workforce development grant that bought these robots from, it's supported by Alabama. And one of the ways to get the grant is we had to buy different robots. Degrees of freedom, are we okay here? Okay, guys, let's go ahead and pause. Let's take. So the degrees of freedom, this is the total number of axes or joints the robot has. It includes the end-of-arm tooling if the end-of-arm tooling is an integral part of the robot. But you won't see that in industrial robots. That's very, very seldom. But in intro, when you was playing around with those gray robots, that gripper was an integral part of the robot. It wasn't mounted on the robot. It was part of the robot. So that would be considered one of your degree of freedom. Gravity less than 3 or greater than 6. But we could have a 7th. We could have an 8. The teeth pendant on the new robot has 8 keys on it for axis. Here we go. This is what type of robot would this be? What work cell would this be? Or envelope? Yeah, this guy's definitely rectangular. So you can't say these are old robots because these are robots that are currently being used. This is a SCARA robot, which is selected compliant assembly robot. What would this guy be? What type of envelope? Cylindrical. It's everything, all the axes are this way. Probably called a jointed spherical because of the joints. We got 1 rotary, we got 2, so this would be a 2. Okay, 3R, because this guy right here can rotate, but it also can go down. So it'd be a linear axis that can rotate, right? You understand? So this would be a what? 1, 2, 3, 3R, P. So these guys are used for pick and place. I think I showed y'all the video. These things are great. This is a Delta robot. Y'all get to see the Delta robot before they took it away from us last minute? These guys are used for packing. They're used for pick and place. These mount overhead. This is a mobile robot. And we're slowly moving to our vehicles turning into these guys right here. There was some city, I forgot where it was at, where Uber is looking at putting driverless vehicles within the next couple of years. Huh? I don't remember. It might have been Philadelphia, but I don't remember the city. So we're looking at these guys. Of course, these guys are used now. Uh, I think I told you about the Minions up at the Detroit plant. Those would be mobile robots. Of course, aerial robots, most of the drones that the U.S. Is flying over there are actually robots. They're programmable. They can be reprogrammed. They can be flown manually, just like we can move these robots manually, or we can program them to fly. A lot of your more expensive quadricopter are actually drones, where you can bring up a map and say, I want to go from here to there, and the thing just does what? Yeah, it just goes. This is a marine robot. So we have quite a bit of categories. Most of ours are fixed or they're on a slide. These are probably the predominant ones, is the 6-axis robot. Delta is really coming into play, especially on food processing and stuff like that. Drive power, are we okay there? Electric, hydraulic, and pneumatic. These are just the robots, right? Repeatability, everybody okay on that? Usually the smaller the robot, the better repeatability it has. The bigger robot, the worse it has because it's trying to move all that mass. Accuracy, maybe called resolution. These guys are not normally specified. So I don't think, if you look doing that research work that you did, I don't think accuracy was specified on anyone that we have. And maximum reach of the horizontal and vertical. This is given in a. This is usually the way they give the envelope. And y'all had to develop one of these. And this is what we were looking for when you had your gray robot. Not only did we draw what it does horizontally, we draw what is vertically, and then what you need to do is we take this and place it on that, and that would be the actual envelope. Of course, we would take an infinite number of these and move it around there, and you can see this right here forms a sphere, right? Jointed spherical, though, the inside usually looks kind of like this, and that's the big difference between a jointed and a regular real spherical robot. Speed, the maximum speed that the center point can achieve, the tool center point can achieve. So speed is recorded relative to the programmed tool center point. So that means if the tool center point is not in the middle of the mounting flange, then we've got to have a method where we can redo that, right? And we'll look at that toward the end of the term. And like I said, we'll set a tool center. Memory capacity indicates the length of the program. Some robot will indicate the number of different programs it can store. For point-to-point robots, which all our robots are point-to-point robots. Okay. This is going to be taught as the minimum, as the maximum number of programmable points. Continuous path robots, those are the guys you move around in these, right? And we showed y'all videos of that. So this would be continuous path. Of course, that video was really neat. Software supported. So these are our programming languages right here. So ABB uses a language called Rapid. FANUC uses Corel. KUKA uses KRL. Mitsubishi uses what they call Malpa Basic. And Motorman uses Info2. Now what it means is you're going to write programs for this, and you're going to be on one of these robots, right? You'll understand that. And these languages are not compatible, which means if you write a program for this one, you can't take the program for the Motorman and put it on a USB stick and go over there to the FANUC and upload it and it run because it speaks a different language. Everybody understand that? But they all do the same thing. So what that means is if you pick up the FANUC then it'll be real easy for you to learn the Motor Man. All you got to do is figure out how the Motor Man does the same thing, right? Does that make sense? And I think I told y'all originally when we started teaching the class, we envisioned that everybody would write programs on every robot. And that didn't work out. We didn't get hardly anything done. Are we okay? So whichever robot you're on, you're going to learn these languages. Of course, we're not going to deal with the Mitsubishi. We're either going to be on the ABB, the Corel, the KUKA, or the Motor Man. And we'll figure out how we'll split up once we figure out how many people is going to show up for the class. End-of-arm tools, most robot manufacturers do not make tools. They make robots. And then they'll either sell that robot to you, and it's up to you to design your own tool, or find a company that will engineer the tool for you, or a company buys it. So our robot, our welding robot is a Fanuc robot, but we didn't buy it from Fanuc. We bought it from Lincoln. So Lincoln is one of the major manufacturers of welding equipment. So Lincoln buys the robot, it builds the work cell for the company, for the customer, right? You understand? Marries it to their welder, and then they sell it as a unit. So if you buy a Lincoln welding robot, it's going to have a welder on it. But when they bought the robot, it didn't come with an end-of-arm tool. That makes sense? What's the other big? Miller. So the two big welding companies in the U.S., we have two, Miller and Lincoln, that are in competition with each other. The big Lincoln plant is up in Cleveland. Oh, you did? We went up there and toured. We had the only robotics class I've had is up there when they bought the welding robot, and we had to go up there, and they gave us a tour of the Lincoln. What was really interesting is that they don't pay their people hourly wages. They pay them piecework. So the number of pieces you get that successfully passes quality assurance, that's what you get paid. Yeah, I know. And if you work over what your production is supposed to be, you can work over and take vacation, so they don't have paid vacation. So what you do if you want to take a vacation is that you just make up time. So, and he said that they had over 3,000 people trying to get into that plant. And he said 90% of the workforce was piece pay. Environmental requirements. Most industrial robots are designed to operate under typical factory conditions. If you're going to run it in a gaseous environment or something like that, then you're going to have a special robot usually made for that. And that's it. So that should be our introduction to get us ready to actually start talking about what we're going to do programming the robot. Now, intro had a lot more to it. All we're trying to do is just get us ready so we can deal with programming the robot, so we can even talk about it. So any questions on anything that we went over? So Tuesday we went around to all the work cells, right? Looked them over, found out where, identified the parts.